Hello everyone, I'm Hu Shenyu from Nanjing University. I'm glad to have the opportunity to share our work. This work is supported by a collaborative project of Nanjing University and OPPO. Today, multi-label image classification systems are everywhere. However, these systems may make terrible mistakes. For example, Google Photos classifies two black people as gorillas, while MSS produced unexpected behaviors because compared with single label image classification, MSS is much more complicated. The output space is huge and the label correlations are complex. To the best of our knowledge, current MSS is based on TNN, and there are lots of studies focused on white box testing of TNN-based systems. However, in the real-world scenario, due to security, privacy, or copyright, the white box information is often inaccessible, and black box testing may be a more practical choice. There are some existing black box methods. However, they don't consider the core functionality of MSS, that is handling label correlations. For test image generation, current work aims to reveal more bugs or improve some coverage. So some images are almost impossible to appear in the real world. However, testers of MSS are more interested in realistic images. For reducing manual efforts for checking test outputs, differential testing and metamorphic testing are widely used. However, they focus on as a correctness of robustness. They don't consider the capability of MSS in handling different label combinations. In this context, we propose atom. When given the label space of MSS, first of all, atom determines label combinations to test. Then for each label combination, atom use image search engine to collect images and input them into MSS. Finally, atom combines metamorphic testing and label information to identify test origin. Actually, the key idea of test adequacy is to determine the set of atoms to be covered. For example, neural coverage determines a set of neurons to be covered. Note that the core idea of MSS is how to exploit label correlations. So, for semantic testing of MSS, we divide the output space by dimension, such as one label, two label combinations, and so on. In the label space of MSS, labels are often with supercategories. It limits semantics of the label. For example, the label apple here, we know it's a fruit, not a company. For each label combination, we use Google Images to collect test images. For better match, we use search operators provided by Google. We provide a keyword pattern to construct keywords. Google will return images accompanied by titles. The title usually describes the content of the image so that it can be used to filter out possible irrelevant image. Specifically, we propose some heuristic rules to help us determine the final test images. One test images corresponding to specific label combination are determined. We input them into MSS and conduct metamorphic testing. Here, we select 7 homogeneous metamorphic relations. The outputs of MSS are supposed to keep unchanged when small perturbations are introduced. If the image pass empty, then we check whether the key labels are recognized. If yes, we think the image is a competent image, which indicates that MSS has a good classification ability for current label correlation. If the images feel empty, they are error revealing images. Then we check whether the error is due to current label combination. That is, we want to check whether the current label combination appears in some of but not all of the 8 outputs, 1 source and 7 follow-ups. If yes, we think the image is a label error image. Otherwise, it's a general error image. For evaluating ATOM, we propose 3 research questions. RQ1 concerns how effective is ATOM in collecting relevant image. RQ2 concerns how effective is ATOM in revealing errors. RQ3 concerns how effective is MSS in handling different label combinations. We conducted experiments on 2 academic benchmarks and 1 industrial AVP. For RQ1, we manually annotated all tested images, and we found that ATOM is effective in collecting relevant images. For RQ2, we can see that ATOM reveals lots of errors when examining 1 and 2 label combinations. We compare ATOM with random testing because there are no existing methods are designed for testing MSS. Experimental results show that ATOM can trigger more diverse behaviors and reveal more diverse errors. In addition, we compare label combinations covered by tested images of ATOM and images in the validating set. We can see that the validating set may not reflect the true data distribution. For RQ3, we define a matrix score, which is the ratio of images on which MSS outputs the current label combination to images relevant to the label combination. The higher the score, the better the performance for the label combination. We can see that MSS remains ineffective even in classifying 2 label combinations. For understanding why MSS make mistakes when classifying specific label combinations, we manually check label error images and summarize 3 possible error types. Error type 1 is caused by the difference in the size of objects. For example, when testing the label combination bicycle bottle, the bicycle is large but the bottle is small. Error type 2 is caused when some objects are in a different form. For example, the sofa shows its back when it appears with a bicycle. However, we often see the front or the side of the sofa. Error type 3 is caused when MSS captures incorrect correlations. For example, MSS outputs data table when there is only a chair in the image. In conclusion, ATOM responds to 3 key challenges of testing MSS, that is, test adequacy, test image generation, and test oracle identification. Experimental results show that ATOM can reveal lots of errors. Feel free to email me if you have any questions. Thank you.